Hello, this talk is about modeling AI components in web architectures, a visual and semantic extension of the Web Composition Architecture Model, or WAM. AI is now woven into everyday web systems, recommendation engines, assistants, classifiers, anomaly detection. But our architecture models still treat AI as a generic box. Meanwhile, governance frameworks such as the EU AI Act, the NIST AI Risk Management Framework, the EU Ethics Guidelines, and the Taylor Handbook all demand transparency, accountability, data governance, robustness, and explainability. Today, those concerns live in separate documents like model cards and datasheets disconnected from the architecture. Our argument is simple. AI trustworthiness should be addressed at the architectural design stage, not bolted on afterwards. Rather than invent a new formalism, we extend WAM. WAM already gives us a compact vocabulary for federated web systems, the elements shown here: services, applications, process units, and data providers, organized into security realms with their own identity providers and connected by invocation and trust relations. Its WAM XML form and the later semantic WAM ontology already made it layered and machine readable, so our AI elements build directly on these familiar symbols rather than starting from scratch. We introduce four AI-specific elements, each a specialization of an existing WAM concept. An AI application delivers AI-driven functionality. An AI service connects to internal or external AI services. And API, an AI dataset, represents the data used to train, test, or evaluate models. And an AI process describes workflows involving AI-specific tasks. As the figure shows, each AI element inherits its familiar WAM symbol, so the notation stays continuous while the AI roles become explicit. Element types alone aren't enough, so every AI element carries typed metadata. Properties have explicit types: string, number, boolean, enum, date, and text area, which keeps editing, validation, and export consistent. The property groups map directly onto what governance frameworks ask for: data provenance and sensitivity, bias and fairness, privacy and compliance, provider information, performance, explainability, and lifecycle. Structure and trust-related semantics now sit in the same model. From one internal model, the editor exports two machine-readable formats: JSON LD and RDF Turtle. A dedicated RDF mapping service aligns WAM concepts with established vocabularies such as schema.org, DCAT, and Brovo, while a custom WAM namespace preserves the architectural meaning. The diagram stops being a static picture and becomes a knowledge artifact that can be validated, queried, and integrated into graph workflows. It's implemented as a lightweight, browser-based editor with a strongly typed data model. We evaluated the approach with 31 participants using the user experience questionnaire, 8 semi-structured interviews, and external validation of the exports. UEQ scores were positive across all 6 dimensions, strongest on efficiency and perspicuity, so the added semantics didn't hurt usability. Interviewees valued documenting datasets, providers, risks, and explainability directly inside the architecture, and the exports held up technically. JSON LD passed a schema.org validator, Turtle passed a turtle parser, and the RDF loaded into Neo4j Bloom and RDF2. To conclude, by adding explicit AI elements, typed metadata, and semantic export to WAM, the architecture model becomes a trustworthy by design artifact, bridging governance requirements and real system design without losing the simplicity of lightweight web-based modeling. Thank you.